Dear students, today I am going to discuss the fifth chapter in first book, that is Magnetism and Matter. The term magnet is derived from the word magnesia, which is an island where magnetic ore was found. So, naturally occurring magnet is lodestone, where a freely suspended lodestone were aligning in the north-south direction. North-south direction only. Approximately magnetic north and geographic north are in the same direction. Approximate, not exactly, because there is an angle called declination. The lodestone, naturally occurring magnet, a piece of stone which used to align in north-south direction. So the people thought that there is some property around the earth. So magnetism is concerned with the earth. So earth's magnetism I will discuss in the next sessions related to earth magnetism. So earth is a huge magnet. It acts like a huge magnet. So magnetic field of earth is very weak, but there is certain magnetic field, there is some attractive property on the materials. Any magnet freely suspended would align in the north-south direction. So magnetic needle orients in the north-south direction. A bar magnet orients in the north-south direction, whereas a lodestone freely suspended also aligns in the north-south direction. So it is not the geographic north and geographic south. All these orient in the axis, that is along magnetic axis, magnetic north-south direction, not the geographic north-south direction. So this idea is used in finding the directions of a place, directions of in a place, used by the engineers to know which direction is what. So it is approximately, that is not exact idea to say geographic north and magnetic north. So it is approximately, we can find out the geographic north using the needle. It is because it is the needle shows magnetic north, not the geographic north. So some basic ideas we will learn in this about magnetism, that is bar magnet and the magnetic fields due to bar magnet, magnetic field due to bar magnet. So basic ideas and some properties of magnetic field lines, unlike electric field lines. Some properties are matching, some properties are opposite in the case of magnetic field lines. So bar magnet. So what is a bar magnet? The magnetic field lines of a bar magnet, how it will be. So this is a bar magnet. If you take the cross section of a bar magnet, okay, there will be two poles, north and south. N and S are the two poles of a bar magnet, and poles means ends. The exact location of the pole is not the end, it is a little inside the magnet. Okay, the field lines of a bar magnet are like this, closed loops. Okay, closed loops, but no intersection of the field lines. Field lines do not intersect in the case of magnetic field lines, and the field lines will come out from the north side, enter into the magnet from the south pole. The field lines come out of the north pole and enter into the magnet from the south pole. The field lines are the pictorial representation of the magnetic field around any magnetic configuration, like a magnet, bar magnet, solenoid, or a straight conductor. So pictorial or graphical representation of the magnetic field. These lines are not real. Those lines do not actually present, but the magnetic field is present. The magnetic field present, how can we represent? We can represent by means of these imaginary lines. You have to imagine lines and show. So that line is there means it indicates the field at that point. Okay. This is a bar magnet. Field lines due to a bar magnet. Bar magnet. Bar magnet. Okay. Then next, the magnetic field lines properties. Magnetic field lines are the pictorial or imaginary representation of the magnetic field around a configuration like a magnet or solenoid, current carrying solenoid. Then some properties of magnetic field lines. Properties of magnetic field lines. Properties of magnetic field lines. The first property, the magnetic field lines do not intersect each other. So we can see in the figure there is no crossover. So one field line is like this and another field line is like this. We cannot show. This is a wrong representation of the magnetic field lines. So they cannot cross each other. So this way of representation is wrong. So if any diagram is given, so question in the CET and other competitive exams, 4 figures may be given in 4 options. Identify the wrong representation of the magnetic field lines, or electric field lines also the same property is there. So magnetic field lines never cross each other or intersect each other. 2 magnetic field lines do not intersect each other when you represent the field. If it's so, if any intersection you show, but assume that there will be 2 directions for the field, which is not possible. A field will have, magnetic field will have a unique direction at a given point, so it is against that rule. Therefore, the intersection or crossing of 2 field lines not permitted when you represent the magnetic field. So this diagram you can see no crossing of field lines anyway. Next, so magnetic field lines do not intersect. Field lines do not intersect each other. Intersect or crossover each other. This is the very first property you can say. Then second property is the magnetic field lines form closed loops, unlike electric field lines. Electric field lines do not form closed loops. They are one-sided. Means the electric field lines start from say positive charge and end at negative charge. Or if a single positive charge is there, field lines start from positive charge, end at infinity. From that positive charge, all directions we show the going out of the positive charge. Whereas only isolated negative charge is there, only one negative charge is there. The field lines all coming into that negative charge from infinity to the negative charge. So terminate at negative charge, start from positive charge. Whereas the magnetic field lines, we cannot say where it starts, where it ends, because it is a closed loop. So here we can say, we cannot say where it starts. We are unable to say where the magnetic field line starts, and because it is a closed loop. If it is one-sided, we can say where it starts. But when it is a closed loop, it is continuous without any break. Okay, so we cannot say where it starts. So magnetic field lines are closed loop, form closed loops. This is the property which is exactly opposite in electric field lines property, where electric field lines are one-sided, start from positive, terminate negative, whereas magnetic field lines are forming closed loops without any break. Magnetic field lines form closed loops, or they are continuous curves without any break. Continuous curves without any break. There is no break at all anywhere, without any break. Okay. Okay, the next property of the magnetic field lines. The tangent to the magnetic field line at any point gives the direction of the net field at that point. There may be many configurations. You can keep two magnets nearby or three magnets or any magnetic material which producing the magnetic field, like a bar magnet or a magnetic needle or earth magnet. And if you have such a 2-3 configuration and net magnetic field will be there, so the needle will show one direction. So that is the net field direction. Magnetic needle will show a particular it orients in the particular direction. That is the direction of the net magnetic field at that point. Same way I can say the tangent. If you show graphically due to 2 or 3 magnets, you are showing the magnetic field line. So tangent to the magnetic field line at any point to that magnetic field line gives the direction of the net magnetic field at that point. Okay. So tangent, suppose in this diagram if I explain, suppose at this point, so tangent to I can draw like this. So that means at this point the direction of the field is this way. Whereas at this point, little away, if I take this point, the field direction is like this. This is the tangent. If I take this point here, the tangent will show this way. That means the direction of the field is this. At this point if I draw, the tangent will give direction this way. That means the magnetic field is along this direction at this point. If I take this point here, the field will be like this. So that means the direction shown by the tangent is the direction of the magnetic field at that point. So tangent to any magnetic field line at any point when we represent shows the direction of the net magnetic field at that point. Then comes the third point. Fourth point is they are continuous curves without any break. I said there is no crossing. The field lines are crowded. Whenever the field is high and strong, the field lines are crowded, and the parallel field lines, if the field lines are represented by parallel lines, then we can say that the field is uniform in that region. The field is uniform means we are representing the parallel lines, and we have to compulsorily put the arrow mark, and also we have to say B vector. B vector represents the magnetic field. Okay, B vector represents the magnetic field. So the parallel lines and equidistant lines, they represent the magnetic field direction. They represent the magnetic field direction. Okay, so that's all about a bar magnet and the magnetic field lines and their properties. So in this topic, next the solenoid. If you pass a current in a solenoid, I have discussed in the previous chapter, moving charges and magnetism. I have discussed the property is that whenever a current is passed through the solenoid coil, okay, so there will be magnetic field produced by the solenoid, and it is very similar to a bar magnet. The magnetic field produced by a current carrying solenoid is very similar to the magnetic field produced by a bar magnet, and the magnetic field inside a solenoid is nearly uniform at the center, and the strength of the magnetic field decreases as we go to the end of the solenoid. Solenoid is a hollow tube, and we may put some soft iron or some materials to intensify the magnetic field inside the core as a core, and outside there will be insulated copper wire wounded very nearby, and which forms every loop is current carrying loop producing the magnetic field. Okay, so that is the idea of magnetic field due to solenoid. Now I will move to the next topic in this chapter, that is Gauss law. So Gauss law we studied in the Gauss's law in magnetism. So it will be very clear in the exam. I don't get confused. Okay, with the question. State Gauss law in electrostatics. We have studied about the relation between the electric flux and the charge enclosed by any body. The net electric flux through a body, charged body, is 1 by epsilon naught times. Is 1 by epsilon naught times the net net charge enclosed by the body. Okay, so the total electric flux through any closed surface or a body is 1 by epsilon naught times the net charge enclosed by the body. So that is Gauss law in electrostatics. Now here in magnetism, the Gauss law is also telling about the magnetic flux. In electrostatics, the Gauss law says about electric flux relation with the charge enclosed by the body, whereas in Gauss law in magnetism says the magnetic flux linked to a body. So what it says, the statement of Gauss law in magnetism, okay, state and explain the net magnetic flux, through any closed surface or any surface is equal to 0. So the idea of flux. So if any surface you take, closed surface, okay, so it has got some magnetic field lines like this. The magnetic field lines are passing through that surface. It may be like a paper piece. So field lines are passing through that surface. Okay, so it is the surface is closed, means with boundary, and field lines are passing through that surface. The field, this body is not having any current or anything like that, only magnetic field I am showing. So small area vector I will take here. The direction of area vector is like this, suppose, and here is the magnetic field line. So the direction between them, angle between them, magnetic field and the area vector, angle between the area vector and the magnetic field B with the angle theta. Okay, the flux through the small region, so magnetic flux through the small area, so magnetic flux is denoted by symbol phi B, electric flux we represented by the symbol phi E, whereas the magnetic flux represented by the symbol phi B. Okay, so delta phi B equal to the magnetic field in that region and the area. Okay, area vector you can take delta A also or delta S also. We have taken as delta S here. Area vector. Area is delta S, magnitude of area, and the direction of area vector is n cap. N cap is the unit vector pointing normal outward from a surface. Normal outward. So that is delta S vector. B dot delta S vector. Delta phi B equal to B dot delta S vector. That is the flux, magnetic flux through the surface delta S, small elemental area delta S. How much field lines enter? That is the B dot delta S, means dot product of B vector, magnetic field at that point, and delta S vector. We can expand this B delta S into cos theta. The area element is taken very small, infinitesimally small area element. Okay, so this is the expansion for the after taking dot product expansion B delta S cos theta. Now what is the net magnetic flux through the entire surface? So this surface has got a large number of field lines and large number of area vector. Okay, so the net magnetic flux through this entire surface, through the surface S, is phi B. Okay, phi B net also we can write, that is summation of delta phi B, where a summation is made over all delta S. Summation over all delta S means the surface is assumed to be made up of a large number of small area element vectors. Okay, area element. It It can be made up of thousands of infinitesimally small area, not this much big. So how big the area element is taken? It is extremely small actually, and only to represent I have shown this much big, and the field is almost same at all points on that area vector. Such a small area vector is assumed delta S. Very small, infinitesimally small. So over all delta S we add the flux through the surface. So total flux, magnetic flux through this entire surface is the summation of the magnetic flux through enclosed by each elemental area. That is the net flux through the surface. And this net flux expansion V dot delta S, okay, over all delta S is equal to 0. So this is important, last one. Over all delta S we are summing the flux enclosed within it delta S, okay. So that dot product or scalar product of the flux enclosed, okay, scalar product of the magnetic field and area vector gives the flux enclosed by the small elemental area delta S. The net flux when added up through the entire surface, that results 0. So why this comes to 0? This is something we have to understand. The flux through the entire surface is 0 because the magnetic field lines, I said, they are closed continuous curves. The field lines entering a surface must leave from the surface. So if the field lines enter the surface, they have to leave from this side, and it goes and joins this way. So if we assume the field lines enter and field lines leave, same number of field lines are entering into the surface and leaving the surface, okay, because whatever field lines enter, same number of field lines leave the surface. If you assume that magnetic field lines leaving the surface is something positive phi, plus phi, and there will be field lines entering, so that becomes minus phi. So plus phi plus minus phi, the net flux will be 0, okay. Phi net magnetic field, the magnetic flux to any surface is due to the flux entering into the surface and flux leaving the surface. One you take positive, other will be negative. So flux coming out we take positive, the flux entering the surface is negative. So net flux through any surface, closed surface, becomes 0. So this is about the Gauss law in magnetism. Okay, Gauss law in magnetism statement is this: the net magnetic flux. Very importantly, you have to write magnetic flux. Okay, so that is the net magnetic flux through any closed surface is 0. Better to say closed surface. Through any closed surface is 0. So the surface is closed with a boundary, and then there is a small area element vector. So state and explain means statement 1 mark. The net magnetic flux through any closed surface is 0. Then explanation, show this diagram. Flux through the small area delta S, infinitesimally small area element. The net flux, this last equation is very important. The net flux through the surface is this much compulsory order. So statement and this equation is enough actually. Okay, net flux. So that means that we are telling how many field lines enter, the same number of field lines are coming out of the surface. So number of field lines entering the surface is equal to number of field lines leaving the surface, hence the net flux through any closed surface is 0. So that's all about the Gauss law in magnetism. Next, we are discussing some of the things related to the earth magnetism. Okay, so earth magnetism. Just let me give some idea about earth magnetism in this class, and in the next class I will discuss all the various elements. So earth is nearly spherical, it is not perfectly spherical. So earth has got its own magnetic properties. So any bar magnet or a needle freely suspended orients approximately or nearly in the north-south direction. So why those needle or magnets orient in north-south direction? This is the question asked. So since BC, something like 2500 years ago. So why? There is some property. Even a natural magnet like a lodestone can orient in a particular direction. So used it by the navigators while going in the ship, because there is nothing other than a magnet or a lodestone. There is nothing else. They cannot simply find out the direction except the sunrise and sunset. There is another way they can find the direction, which is north, which is south, which is west and east, only based on either magnetic direction or the sunrise position. They can say which side is north and to where they have to lead, where they have to reach. Whereas this magnetic ideas or needle shows the direction. So that why it shows, this is the point. So there were many theories related to this Earth's magnetism, to explain the Earth magnetism. But right now we are taking the theory called dynamo effect. So the Earth magnetism is because of the convectional current of the fluids, metallic fluids in the molten state, such as iron, nickel, cobalt, etc. They are all magnetic materials. Iron, nickel, cobalt are the magnetic materials. They have the magnetic properties. Whenever they brought near the magnet, they will be attracted strongly, okay, especially the iron piece. So it becomes, or it can be easily magnetized, and those materials are called ferromagnetic materials. And then the magnetism actually originates from the domain theory, and every molecule has got electrons, and that electrons property, electrons in their orbit, okay, there is a thing called magnetic dipole. So the basic origin of magnetism is nothing but the electrons motion. It is the spin motion we say, and the orbital angular momentum is also giving certain magnetic dipole. That is the origin of the magnetism. That means electron revolving in the orbit will have certain magnetic dipole moment, and there will be many electrons in an atom, so revolving, so that is the net magnetic dipole is produced. Okay, so a little more theory we studied in chemistry regarding this magnetism. So it is the electron motion. Ultimately we can say electron motion is making the molecule as an electric dipole, because in the previous chapter we have studied briefly about the even one derivation was also there, that is saying the magnetism or revolving electron is equivalent to the dipole and Bohr magneton we have studied. So the cause for magnetism in any atom or molecule is electron motion, orbital motion and spin motion. Both are there. Magnetic dipole moment is there for that. And then now the Earth magnetism is explained based on the dynamo effect. Dynamo effect means the convective motion of the metallic fluids, such as metallic fluids, iron, nickel, cobalt, all that constitute the convectional current, and that current gives the Earth magnetism. So it is like a bar magnet. Earth acts like a bar magnet, but there is no such bar magnet present inside Earth. The bar magnet configuration and the field lines of Earth are approximately same. So dynamo effect is the main reason, and the magnetic field strength of Earth is about 10 power minus 5 Tesla. It is very weak, okay, very weak magnetism or magnetic field is produced by the Earth. And later in the next session I will discuss about the Earth magnetism terms like declination, inclination and horizontal component of Earth's magnetic field.